So welcome to another episode of your favorite TV program, CS340. I'm your host, Frank. This is your co-host, Payman, and I look forward to another enjoyable hour together. Today we'll talk about k-means, clustering, but only after we sort of solidify our understanding of random forests, which we covered last time. So we talked about ensembling, different kinds of ensembling last time in order to improve accuracy without hurting too much in terms of overfitting. And random forests are one example of an average style ensemble method, which basically averages the results of fitting deep random trees to bootstraps of data. So we get random trees. We've focused so far on bootstrap sampling in order to get trees that are not the same. We're going to talk today about one more way to make the trees even more random, and thus their errors are more independent. So the randomization encourages the errors of different trees to be independent, right? And just to be brutally clear about what's going on, right? We have our training data, X and Y. We do some sort of bootstrap sample 1, 2, 3, however many, right? This gives us 3 different data sets, and on each of those, we fit our favorite deep decision tree. Right? Okay. At test time, we get some new feature vector that we'd like it to assign a label to. We take it and shove it through each of the decision trees that we train. This is the forest, obviously, that forest of trees. Each one makes some prediction, maybe the spam or not spam in the case of email classification. And then we average the classification results by, in this particular instance, taking the median score. So there is one more way to enhance the randomization of the learned trees, or rather make the trees errors more independent. And that is to, while training each individual random tree, and this is a critical part, for each split, what you can do is actively not consider some subset of the features. So you can randomly sample a small subset of the possible features. So if you have D features total, maybe you only look at square root of D features, right? So that's a pretty small number in comparison to the total number of features, and only consider those random features when searching for the optimal decision stump rule at that node in training the random.
What's the difference between cross-validation and bootstrapping?
Yeah, that's a bit of an odd question at this point in what I'm talking about, but yes, cross-validation when we're searching over the best possible decision tree hyperparameters would look at all of the it would look at all the training data through the fold mechanism. Yeah, exactly. But bootstrapping has nothing to do with that, really. Yes, I think Akeem, the way you wrote that there is exactly right. So cross-validation, if that's the spirit of the question, yes. Cross-validation is used for hyperparameter selection or model selection, or validating the accuracy of the model before testing it, and bootstrapping is just used during training. That's correct. Yeah. In other words, when you're doing cross-validation, you're going to train, and when in each one of the cross-validated folds, when you're training, you're going to use bootstrap sampling in order to train. That's the other way of looking at it, right? Okay, so back to what I was talking about. So when you're building your random forest and you're training a random tree on a particular bootstrap sample, right? You also, when fitting the decision tree, consider again only root D features at every decision stump optimization choice. Okay, so here we only, for instance, look at, if we're thinking about the allergy example, milk and oranges. Here we only look at eggs and peanuts. Here we only look at lactose and gluten, so on and so forth. And over here in the other tree, you choose a completely different subset, root D size subset of the features at every decision stump optimization step in the tree growing algorithm. Okay. Of course, when you do this, the splits will tend to use different features and different trees. The trees will still overfit, particularly if they're deep, but the errors that they make will be more independent. So the average will, like we talked about before, tend to have much lower test error, excuse me. So empirically, and this is important, and this is something that says something about nature and the compatibility of random forests with natural data sets, right? Random forests have been empirically demonstrated to have one of the, or to be basically one of the best out of the box classifiers, right? So there's a paper from 2014, which established sort of a baseline data set of data sets. So in other words, there's 121 data sets, it's classifying whatever, 121 different problems. That doesn't really matter, but they're drawn realistically from the set of things that people use classifiers for. And they actually compared 179 classifiers and basically fit 179 classifiers on 121 data sets, and did some pretty extensive tuning and that sort of stuff. And it turns out that out of all those 179 classifiers, probabilistically, if you were to ask, what's the if I were a betting person and I needed to bet about which one of the classifiers would do the best on those data sets, you should bet on random forest if you choose to back the one that's going to win most often. Random forests are most likely to be the best classifier, which is kind of an interesting statement about reality and the kinds of and the nature of classification function relationships. But that's it. So yay! Actually, however many people are, 66 people have managed to stay with us today. About half. That's about right. We made it somewhere. Congratulations! Right. I can never remember how many parts there are in the course. Are there 4 or 5 parts in the course? Damon, do you remember? Yeah. That's the uncomfortable laugh of I don't remember either. Yeah, some number, 4 or 5. I don't remember. If you only choose between random thresholds next, would this also help independence in lower test error? Mallory, interesting question. If you chose random thresholds, then you would have random trees. Right. Now, there's some work. A friend of mine, Joshua Vogelstein at Johns Hopkins, I think, wrote a paper called "Randomer trees" as a little bit of a play on Dumb and Dumber and Dumb and Dumber, I think. I think for our purposes, you should not think about random thresholds, because random thresholds, well, yes. Okay, yes. The short answer is yes, you could imagine that's true, but the individual trees would not fit as well. So the individual trees would not perform as well. So there's a little bit of a trade-off here, because for the averaging to really work, you want the individual trees to actually to fit their subset of the training data pretty well. But if you make random thresholds, then it's not clear that you'll actually achieve that, but you can mitigate that by making the trees deeper. It's all a much of a muchness. So here, Mallory, I think you want to look at randomer trees if that's of interest to you. Jovo, good old Jovo. Anyway, so we're done with part 1. Yay! However many parts we have, we've made it somewhere, and we've actually covered a bunch of really fundamental concepts that will stick with us through the remainder of the course and through the remainder of your life and career as you consider and maybe do machine learning type things, right? So some of the fundamental ideas are that the difference between training and test error, right? It's sort of obvious, but like one is memorization, one it's really the difference between memorizing, like just not actually generalizing at all, and learning. We care about the test error, not the training error, right? We've talked about independent and identically distributed data, what that means, and in terms of being able to learn anything, right? The underlying assumption that we're making is that the examples, test, training, and validation all come from the same distribution. Otherwise, there wouldn't be really anything to learn, and you couldn't generalize from one to the next. We have the golden rule of applied machine learning, which is that the test data should not influence the training procedure that you use in any sort of a way. We talked about the fundamental trade-off, which is really about overfitting, right, between training error and approximation error. You can push the training error really low, but that could lead to an increase in approximation error. We talked about validation sets and the cross-validation procedure, which is you're going to use over and over and over in your career. And we showed how this can approximate test error. We discussed optimization bias, which is to say that we can overfit both the training set and the validation set, particularly if we look at the validation set or the training set too often, right? We just did a teeny tiny little bit of decision theory where we said we should, in certain circumstances, actually consider the costs of the predictions we make in addition to just their probabilities and getting the test accuracy minimized. We introduced a notion that many of you are probably not familiar with a priori, which is the notion of a parametric versus non-parametric model. And in this course, we talk about non-parametric models as being those in which the model size depends on n. So k nearest neighbors, the program that we induce has all the data in it, so it grows as n. And we have had to remind throughout various questioning, and we will need to address this over and over in the course, which is that there is this no free lunch theorem where there is no best model. So you can't look at a data set and then just say, hey, this is going to be the best model for this particular data set. You have to actually try a bunch of stuff and see how it does. Cool. Any questions at this point? Because yeah, we made it somewhere. We've got some stuff, right? And you're even getting to be useful. Random forests and decision trees and k nearest neighbors and naive Bayes. You can do some stuff. It's pretty cool. So questions, comments? It's weird to try to focus and like actually look at you. I don't know how many of you actually look at me while I'm speaking, but I sometimes want to look at you, but I can't see the chat and payment, and so I do my best. It's not it's not high production values, unfortunately, yet. Okay. Why are all the scikit-learn models so much faster than yours? Well, Alan, I'm not going to cast any aspersions about your coding skills. A lot of it has to do with the fact that you guys use Python looping and that sort of stuff rather than calling into an underlying C implementation or something. And the first assignment we used the built-in model from saying, what underlying model did it use? That's a good question. Do you know the answer to that one, Payman?
Built-in model, what underlying model? I don't remember, actually. I have to check now. I don't remember.
Payman, you look that one up and we'll get back to
yeah.
Tianyi, can you rephrase your question? What makes the ML algorithms different than non-ML algorithms? I don't understand that question. I'm sorry, maybe you rephrase it. What I'll say in response to that, maybe this will make sense, is that, well, let's be careful to not conflate two things. One, we're going to talk about machine learning models, and then we're going to talk about algorithms for optimizing objective functions that correspond to the models that we consider. So when we talk about algorithms, we talk about, generally in this course, we talk about specific algorithms for optimizing parameters of some model. And what makes them different is that we're talking about specific instances of algorithms bespoke to the models we're talking about. But non-machine learning models for optimization or optimization algorithms or convex optimization algorithms, combinatorial optimization algorithms, so on and so forth. There are general classes of those, and they can be applied to machine learning models. And one of the things that you should be thinking about in the back of your head while you're listening to this relatively high-level lecture series is, in fact, that when I say combinatorial optimization, I'm giving you a big hint that the kinds of algorithms that you can apply are any combinatorial optimization algorithm you might have in your toolbox to solve the problem. So we're giving you specific instances of algorithms, but there are other algorithms that you can use to do the optimization, to solve the optimization problems that we'll encounter in the course. Hopefully that helps. N, yes, indeed, that was answered. So Sean, what does N mean again for the second to last point? N means the number of data items, size of the data set in terms of the number of samples. Okay, great, let's move on. Oh, well, not quite yet, because we talked about one more thing. We also we saw like 3 ways of learning, and this is important, right? So what does learning mean? It means generalizing, but we conflate learning with the optimization algorithms we were just talking about, right? So we're still trying to do program induction, right? In decision trees, we looked at combinatorial optimization algorithm, basically that did greedy recursive splitting and did optimal local decision stump finding at each greedy split. So we searched for rules. We did some conditional probability density estimation by counting frequencies to compute empirical probability estimates, right, for naive Bayes, right, which is a probabilistic classifier based on conditional independence. And we did some, discussion about norms and how to measure distances in high-dimensional vector spaces that are sort of application dependent or like that you can choose, 2 norm, 1 norm, so on and so forth. And then we introduced k-nearest neighbors, which is a non-parametric classifier with some nice theoretical properties. And we saw a couple of generic ways of improving performance. So we encouraged invariances with data augmentation, like shift, scale, warp, whatever, and for filling out feature space for an image classification problem or something like that. And we talked about ensemble methods, highlighting random forests yesterday and today. Cool. Let's switch gears. And I said at the beginning that we talk about unsupervised learning. So let's switch gears and talk about a couple of applications maybe in unsupervised learning, and it'll be clear what I'm talking about in a little bit, if it isn't already. So let's say that this is 1,000 here. So X, we're going to get X as 1,000 different types of cancer cells, and we get a whole lot of gene expression data for each of those cells. Okay, so I don't know how many genes there are. I don't really know anything about genomics, anything about this. However, I might be asked as a machine learning practitioner / expert to say, okay, can you tell me, here, I care about cancer. I know what genes are. I know what gene expression is. I know how many I know, like, I've collected a bunch of data. I can give you a matrix like this. Can you tell me how many different classes of cancer there are? That's a pretty standard question you'll get asked. Okay, unsupervised learning is the name given to the class of tools that allow you to address questions like this. The critical part is, and this is what distinguishes supervised and unsupervised learning, is that we are not given the class labels Y, but we want some sort of meaningful labels, right? So this, how many different types of cancer or classes of cancer are there is an example of this kind of quote unquote unsupervised learning. So let's just say it again, right? Unsupervised learning, as opposed to supervised learning. In supervised learning, we have the features X, right? And we have the class labels Y, right? And like we said from the very beginning, what we want to do is we want to, structure and then find parameters of programs that produce Y from X, right? We want to map from X to Y, right? In unsupervised learning, sometimes frustratingly, we only have X values, okay? We have no explicit target labels, but we still want to be able to do something with them. And the kinds of things that you might want to do are actually pretty broad, right? So you might want to say, is this a normal xi? And that question is really a question of outlier detection, right? You might want to ask whether or not examples are similar to one another. So that's similarity search, or which examples look like this xi. You might want to figure out association rules, like which features actually occur together. You'd like to learn latent parts models or latent factor models of your data and ask what parts are the xi's made from. You might want to take a really high dimensional vector space and visualize it in a way that gives you additional information. So what does my high dimensional X look like? And this is sort of like when we're doing the scatter plot array thing, you want to look at your data, you might want some other richer kind of visualization tool to look at your data before you start doing machine learning. You might want to rank your x's, like which is the most important one. Well, the one we're going to talk about is what types of xi are there. Okay, so like let's come up with a classification automatically for these xi's. And I'll just put this out there for those of you who, like me, are less inspired by machine learning and more inspired by artificial intelligence. Those of us who work on artificial intelligence largely focus on unsupervised learning because that's actually how we learn. We don't get a supervisorial signal. We just get observations of the world. We have to make sense of the world, act in the world, so on and so forth. You can argue the reward is a form of supervision, and that's not unreasonable. But then you have to argue about from whence does reward come. That doesn't need to land for basically anyone, but if you understand what I'm talking about, good on you. Okay, so clustering, that's what we're gonna do, all right? Here's the problem setup. You get as input a set of examples described by features xi. Basically, you get a bunch of feature vectors, right? Like usual. And the output is an assignment of examples to groups. Okay, and that's a little bit subtle. It's more subtle than you think until you start really thinking about it. But because there's the output is they're equivalent sets if you permute the labels of the groups. But the point is that you want to somehow associate like items together, and basically you'll do that by giving them the same label, although the actual value of that label might be different from one clustering algorithm to the next. So unlike in classification, we are not given the groups. That's the whole point, right? So if you're doing classification, really, you can think of the label as a grouping, right? Zeros and ones, spams, not spams, as a grouping, right? In clustering, you're not given that, right? What we have to do is we have to discover the groups, right? If you take in the email example, all of the spam emails, right, and ask what types of spam emails are there, that implies that there's some further clustering of the spam emails, and you'd like to work out what they are, right? So there might be the quote unquote lucky winner group of spam emails, or the weight loss group of spam emails, or I need your help group of spam emails, or mail order bride group of spam emails, or enhance various aspects of yourself spam email cluster, so on and so forth. Okay. But like usual, we're going to start with
Did you catch the question?
I will, but it's like I saw you zoning out, so pay attention to the questions, and we missed one from Ramon, but we'll go back to that at the end of class if that's okay, Ramon. So Alan said, could we still cluster emails and hope for a spamish cluster, even though we would have to decide that is what it is? That's a really, really good question. So in other words, if you ignored the labels, it would be really cool if let's imagine we're on Mars and Martians actually exist and they have email, right? And we don't know their language, you don't know anything, right? It would be really cool if, we could take all of their emails and then find two clusters and establish that there's Martian spam cluster, spam email as well, right? That could happen. And it's likely under some clustering algorithms, it might, because there's statistical dissimilarities between spam email and regular email. Less as spammers get more sophisticated. But yes, so you would still have to then look at that's exactly the point. You would have to look at the clusters and then decide which of them is spam, right? You could say that there are two clusters, but you don't know what they are. And then you have to go in and inspect those clusters. And that in and of itself is a little bit complicated, but we're just going to say, let's go find those clusters. Okay. But it's a good point that you're right on target there, Alan. So we'll start with a simple example just to give you a sense of what's going on. So we have some data matrix X, right? It's two-dimensional, right? That's, features and, D features and examples as always, right? And the basic idea behind clustering is basically inspired by human perception, really, like, and the kind of abilities we have to detect different densities and clusters of things, right? So if we just plot feature 1 here and feature 2 here as always, right? Then you get a bunch of black dots, right? And what do you see? Payman, what do you see?
I see a bunch of dots, different divide, but like I see like 4 groups basically.
You see 4 groups, yeah. I mean, almost everybody sees 4 groups. If you get really persnickety, you might say there's a group there. So, you know, you could say you see 4 groups or 5 groups or something like that, right? Cool. We see some stuff that's close together, and we see some stuff that's further apart, right? And we naturally see these clusters without really much difficulty. Okay, so what we see is something like this. We intuitively know that there is this grouping of data items. The problem is we're not going to be able to see it in really high dimensional feature space, so we're going to have to do something different, but we see this intuitively. And what we desire is an output from some algorithm that assigns some numeric label to each of the clusters, right? Such that all the items in that cluster have the same ID. That's it, okay? And here the ID is color and shape coded. But again, just doesn't want to force it, like just say it too many times that it's annoying. We do not have these. These are the things that we derive. We're going this way, right? And we don't have a test error. We don't have the labels, right? The general goal of basically every clustering algorithm is that examples in the same group should be similar and examples in different groups should be different, right? Duh. It should be clear though that like what the best clustering algorithm is hard to define. We don't have a test error. We don't have something against which to judge our progress. So there's basically no best method per se in unsupervised learning. There are lots of methods, and we'll focus like usual on the important or representative ones. And why would you cluster data? I mean, again, there's lots of reasons for it. Like you might want to know what the groups are, right? If you're Adobe and you have a bunch of customers and you see them behaving with your software tool chain differently, in other words, you're like looking at their keystrokes and what they actually do in an application, you might like to know that you have creative professionals, designers, educators, and so on and so forth, so that you can build email marketing campaigns for both of them, or help sections for your website for each individual cluster, right? You might, if you get a new customer and you see with them behaving, you might want to know what group they're in. You might want to say, this person is a creative professional and we're going to target them like a creative professional, right? You might want to find examples related to a new example. In other words, you might want to find other people or users that are similar to that example. Or you might want a prototype example for that group. You might want to go out and like identify somebody that's like, this is the person, or this is the characteristic of this group of users. You know,
in a clustering algorithm, if distance is a measure of similarity.
Shauna, just give me a little bit. We'll get to it. I'm not that far behind schedule. Yes. So in short, the distance is a measure of similarity. Indeed. Yeah, we'll get to it. Okay. We won't belabor this application, but you might want to identify different groups of genes that are active or more or less active at different times in a cell's growth, or at a different cell growth stage. So again, I don't know a huge amount about this application, but it's the kind of thing that gets put on my desk all the time, right? So here are 48 genes, here are 232 genes, here's 111 genes, 35, 144, so on and so forth. And these are 4 independent cell lines for each of a different set of growth, stage of growth. And basically we have a feature vector, basically the expression level for 4 replicates of 3 different cell stages of a whole bunch of genes, right? And you would not see this entire table in this order, right? You would just get a bunch of stuff. And what you want to do is you want to say, oh, look, these particular genes all have a similar expression pattern or change in expression pattern over the life lifespan of a particular cell line. These are active very early in the cell life and turn off. These are, turn off later on. These turn on later, so on and so forth. And I might have gotten the sign wrong. I think I got the sign wrong. Doesn't really matter. But the point is, you want to see that these genes basically have similar functional roles, and you can get this by clustering the genes based on their expression over the lifetime of the cell, something like that. Okay, cool. Lots of clustering, lots and lots of clustering applications. Take star spectra, right, and cluster the star spectra. How many different types of stars are there, right? In biology, are there subspecies, right? In other words, you take all sorts of gene expression for, a particular kind of fly that you observe in the world. Maybe there are 2 clusters, and those actually correspond to 2 different species. You don't really know. You can't tell the difference in just looking at them, right? What kind of documents are on somebody's hard drive, right? If you take bag of words representations, and how many different kinds of documents do you have? Well, you should be able to figure this out by clustering feature representations of the documents that you have on your hard drive. Like what kind of customers? I already covered that example, right? So k-means is so simple, and it's a very popular clustering method. The input, basically the hyperparameters, in some sense, are the number of clusters k, that's a hyperparameter, and an initial guess about where the mean of each cluster is. And basically the way you get a guess for something like that is you just pick 4 of or however many k of the data points at random. You say those are the cluster centers, and you start from there. So the algorithm couldn't be easier, right? You assign each feature vector to its nearest mean, and nearest is going to be some distance, and it's going to be measured similarity, so on and so forth, right? Assign each x to its closest mean. Then you update the mean based on the assignment. I should say assignments, right? So you're going to assign all the data points to the nearest means, and then for all the data points that are assigned to a particular mean, you recompute the mean based on those assignments, and you repeat until convergence. Okay. So here's a k-means example. We have the same data matrix, right? Black dots all over the place. And now we start with k initial mean. So here's 1, 2, 3, 4 initial means, and k equals 4 in this case. Okay. Now what's going to happen? The algorithm we just said, we're going to assign the nearest points, right, to that cluster mean. So all of these are going to go with the pink one. All of these are going to go with the red one. What happens to this cluster is a little bit weird, right? So it's probably going to split like this. So all of these are going to be blue, and all of these are going to be green. Okay, and that's what happens. Okay, so you assign your data points to the nearest cluster means. Okay, and you probably lost track of the original means. They're in these positions, right? So now, after you've made the assignments, you update the cluster mean. So the cluster mean of this is going to go here. The cluster mean of this is going to go here, and the red and the purple are going to stay roughly where they are. Yeah. Okay. Then you do the reassignment, right? So more of the red here is going to be, more of these points are going to be assigned to the red, right? And you keep repeating this process over and over. Update the mean of each group, assign each example to the nearest mean, update the mean of each group, assign each example to the closest mean, and stop if no examples change groups.
Is there 4 inputs for this example? K equals 4, 5 inputs?
It depends on dimensions, Vincent. That's a good question. So I guess the dimensionality of the input would be K, which is an integer, and then in this particular case, each cluster center is 2-dimensional. So this would be a 9-dimensional input. Yeah. Mallory, good. In it just closest Euclidean distance, you can decide a norm based on application. Oh, everybody's got their thinking hats on today. This is great. Yes. So we're going to talk about Euclidean distance, but indeed you can choose a norm based on whatever you want. Oh, there was a no. So Shaunak, I want that I wish I could just remove your comment about is k nearest neighbors a clustering algorithm? No, it's not. That's it's very easy to confuse because the names k nearest neighbors and k k-means, k-nearest neighbors classification, k-means clustering. Okay. Possible. Leo, great question. So is it possible that this algorithm never terminates because data between two close groups keeps oscillating between the two groups as their means update? No, and we'll give a sketch proof of that in just a little bit. This algorithm is guaranteed to converge when you use Euclidean distance. How do you decide which k to put in? Tiani, when we talk about the objective function, remember we said that k is a hyperparameter, which means that we can adjust it using some sort of hyperparameter optimization. However, there's a subtle thing in clustering, and we'll get there just a little bit. So I'll ask you about that. And then, yeah, the same thing with Ramon. That's true, but it's subtle here. It's quite subtle, and we don't actually really address the selection of k in this lecture. Quite right. So, or quite enough. So
test error in this case.
Exactly. So this is the issue. So let's get to the objective function, and then we can make fun of the objective function or think about it. So exactly. So k-means issues. One, great question about convergence. It's guaranteed to converge when using Euclidean distance. If you're given a new test example, it's pretty easy. You can decide the nearest mean to cluster it. Of course, k-means assumes that you know the number of k clusters, the number of clusters k. I did a lot of work in my PhD on picking k, and basically it all is kind of frustrating, and it basically boils down to heuristics, and none of them are satisfying really at all. There's even some pretty deep theory about information theory concerns and like transmission of the model complexity and these sorts of things. But at the end of the day, when we do the hyperparameters, which if we want to select k automatically, we have to do some sort of penalization, and it's largely heuristic. The reality is that in most cases, when you're doing clustering, you kind of know what you want, right? You have like a capacity to deal with the number of clusters that you actually find. Like what is your marketing budget? What's the maximum number of customer classes that you could possibly accommodate, right? So of course, also this is a hard clustering. It's not like there's no way that a data point can be assigned to more than one cluster, right? So you can't have overlapping clusters, or there's no accommodation of quote unquote outliers in this k-means setup. Of course, even though the algorithm will terminate, and we'll give a little sketch of that in a little bit, there's no reason to suggest that it will terminate to, even for a fixed value of k, the optimal solution. We haven't said what optimal is, so just have to be uncomfortable with the fact that k-means may converge to a suboptimal solution. In the prosaic, like qualitative sense, k-means can very easily converge to an answer that looks like this, right? On the exact same data. Yep.
Could we build a distribution based on distance from the means?
Oh, Alan, oh. You should take 440. So clustering from the probabilistic perspective is an instance of mixture modeling. Mixture modeling with Gaussian density assumptions about the distribution of points within a cluster is called Gaussian mixture modeling. And excuse me, Gaussian mixture modeling implicitly builds a normal density estimating the distribution of points within a cluster. So yes, you could build a distribution based on distance from the means. And if you've made that distribution a Gaussian and you change the algorithm to be expectation maximization, you would be doing clustering in a Gaussian mixture model. And if you take hard limits of a couple of processes inside of that, k-means is a simplification of that algorithm. Great. So this is a qualitative idea of what suboptimal convergence is, right? It shows up in the loss function as well, but k-means can definitely do this, right? So the classic approach to dealing with this is basically to do random restarts, right? So you're gonna, when you do k-means clustering, you need to be aware that there is k-means, we also kind of hide under the rug that the k-means clustering algorithm that we've just described is also a greedy optimization algorithm because it's actually a combinatorial optimization problem that we're trying to solve here. And the step of assigning each item to its nearest cluster center is a greedy approximate, a greedy step in an optimization algorithm. Okay.
Could K-means work with non-standard distributions? Like a donut and the whole inside.
Okay, so Christopher, thank you. This is a good question. Let's leave the probabilistic stuff aside. We're not gonna talk about that. But you could, even in a non-probabilistic setting, maybe you don't mean distribution in a probabilistic sense, but if you, for instance, had distance functions that were really wonky and you knew that one class was donut shaped and one class was hole shaped, you could build a distance function for one of the classes, which is zero, which is infinite in the hole and small in the body of the donut, and so on and so forth. So you can accommodate that with just different distance functions, although all of the theoretical guarantees of k-means would go out the windows. So don't confuse k-nearest neighbors classification with k-means clustering, right? It's easy to get them mixed up because of the name, right? So k-nearest neighbors is a supervised learning problem. You're given the label. The meaning of k and k-nearest neighbors is the number of neighbors to consider. K-nearest neighbors requires no training. K-nearest neighbors is complicated or has complex decision boundaries. When k is small, you only have to look at one neighbor, so your decision boundary can be very complex. And if k goes to n, then you just return the class mode, the mode of the class, the training class labels. And k-nearest neighbors classification is non-parametric, it stores the entire data. K-means clustering, on the other hand, is unsupervised. There's no yi, right? K-means the number of clusters. K-means is super sensitive to its initialization. K-means models are simple for small k, you only have a few cluster centers, and they're super complicated for large k. And you should think about what the largest k is that makes any sense at all. And k-means clustering is parametric. For any k-means algorithm that has k not depending on n. And what you store are the means of each of the clusters. So this W matrix here is just the means of all of the clusters. You have k d-dimensional means. Okay. So what is k-means doing? We've given you the algorithm first rather than the loss function. But if you can think about it the other way, you can say, okay, and this is actually how machine learning people really usually think. They say, okay, what's the loss function? And let's figure out how to optimize the loss function. In this particular instance, we've done it the other way around because it gives you a more intuitive sense of what's going on when we're talking about clustering. But k-means, we did not just interpret it, but k-means is a greedy algorithm for minimizing the following objective. Basically, the objective is the total sum of square distances from each example xi to its center w y hat I. Okay, so this notation is a little bit new, but basically it says y hat I is the label that we're going to, it's one of our parameters. It's the class ID of, it's the cluster or the class ID of example I. So y hat I is in 1 to k, is in the set of integers 1 to k. And this just indexes one of these mean vectors, right? Okay, cool. So if we sum this over n and we compute some sort of distance, here's the L2 norm squared, then we can see that the model parameters are the mean vectors, these guys, and all of the assignments for all n objects, right? And if you stare at this long enough, it's one of my favorite, if we were doing traditional exams, this is one of my favorite exam questions, is to say, okay, this objective is differentiable with respect to what, right? So it's smooth and differentiable with respect to these guys. It is non-differentiable with respect to these. So this is the combinatorial optimization problem we're talking about. So if we really wanted to optimize this, we would have to consider every possible permutation of labels, assignment of labels, right? And then optimize the weights for that and then pick amongst those, right? So again, this W matrix is just the d-dimensional cluster means, and there are k of them, right? So k-means steps, minimize f in terms of the y hat i's. That means updating the cluster assignments, right? That's the greedy step. And you want to minimize f in terms of the cluster means. That's updating the means. And in fact, actually, if you take the derivative of this with respect to one of the cluster means, set it equal to 0, solve, you'll arrive at the update mean step. Okay. So the termination of the algorithm, the fact that the algorithm terminates follows because no step increases the objective, right? And there are only a finite number of possible assignments to k clusters. So pretty much that's the proof sketch of the termination of k-means, the algorithm we're talking about. So one thing that you can do, which is pretty nice, so if you fix the value of k, right, then you can use f, this loss function, to choose between different initializations. So this is how you can get away with a random restart. So if you randomly restart for a fixed value of k, you want to choose the restart that minimizes this loss. Okay, that'll be the best clustering under our model, right?
Is the termination also based on the function being convex in W?
That's the never increases the loss part of that sketch proof. So yeah. We should note that the update to the cluster means you will need to change if you use different distances, right? So that should be pretty clear, right? When you minimize f in terms of the means, I already gave you a method for deriving the update, which is basically to solve the gradient fixed point equation. But if you choose, like for instance, the L1 norm, the solution to that fixed point update is to say, for instance, set the cluster mean to the median, but you have to derive that basically for each of the different k-means, objective and yeah. So the cost of computing k-means, we don't know how long it takes to terminate necessarily, but we can talk about what one step looks like. So the bottleneck of k-means is calculating the distance from each feature vector to each mean, right? So each of those is a d-dimensional vector, right? So, and you have to do this for all k-means. So every time we compute the distance to one of the k-means, we have to do d operations, and we have to do this for all n examples to take to each of k clusters. So the total cost of assigning examples to clusters is ONDK, which is not so bad if k isn't too large. Updating the means is cheaper, right? You just have to look at all the examples and sum them up basically for to compute the means. We don't know how it terminates, so how long it takes to terminate. So the per step computational complexity is dominated by ONDK, and that's the end of the story. So yeah, this is just a mean update. It's sort of obvious, right? You just sum over the objects in the cluster and then divide by the number of objects in the cluster. So we'll just say a couple words about vector quantization. I think we're running a little bit behind schedule. I'm not sure why. Maybe too much time on answering questions today. K-means originally comes from the signal processing community, and it's designed for vector quantization, which basically says replace the examples, all of the samples that we have, all the feature vectors, with the means of their clusters. Okay, and there are some examples of this, like Facebook summarizes many locations with a few summary locations. You know, clothing and footwear manufacturers build certain integral sizes. They don't build a continuum of sizes. You know, you can think of, you know, the flavors of ragu as some optimal quantization of, you know, Western people's ideas of what is tasty in Italian food flavored substances. We can do vector quantization to label players based on how many shots they take in the restricted area, which is near the basket, versus the number of shots that they take that are unassisted. And you can put Allen Iverson over here in the creative scorer bucket or something like that, right? You can basically replace all of these clusters with exemplar players. And vector quantization is like, it's clustering, right? Here, there's nothing on this slide except we take our original data, we run k-means. This gives us a lower dimensional representation of the data. Okay, and that's going to be a little bit weird to think about, and we'll get to it later on. But the point is, basically, to represent the entire data set, all you need now, if you don't care about the variance about the cluster mean here, all you need are the cluster means and the labels. And you can use that to approximate the data set or approximate each data item by just looking up in this set of exemplars which each object is a member of, and then use the corresponding cluster mean as as that data item, right? Okay, so this is going to show up when we start talking about parts-based models and PCA and these sorts of things, and you can think about what's going on as kind of a data set compression technique that could make it easier for you to learn models that generalize, because maybe we don't really care about the specific exact value of something, right? If we wanted to build a classifier of this data at some point, right, or build a classifier on this data, then maybe actually the fact that it is one of these clusters is enough for us to make our decisions, right? Is all learning compression? I'm not even going to touch that one. There's a large school of thought that suggests the answer to that is yes. Okay, you can think of political parties as quantizing people's voting preferences and that sort of thing. Okay, so just a little bit past time, but I think we're okay. In summary, random forests, one of the best out-of-the-box classifiers. It's about bagging of deep randomized decision trees. Fine. We finished the first pass through supervised learning. Now we're on to unsupervised learning, which is about fitting data without explicit labels. Clustering finds groups of related examples. K-means is one algorithm for doing that. It's very simple, and it's sensitive to initialization, unfortunately. And VQ, vector quantization, basically builds low or reduced dimensionality representations of the lossy, low dimensional representations of the data by replacing data items with the means of their clusters. That's it.